If you consider the theory has two aspects. One of them is combinatorial and the other is structure. So you have PI-Algebras. They have two components of theory. This is combinatorial theory. We have also structure theory. And if you write them as in this way, you have something like this. So this is combinatorial, and this is structure, and they have some intersection here. So my plans initially were to have only combinatorial theory, but after some consultation with Michel and with Erhard, we decided that it's better to have at least some taste of structure theory. Also because a lot of combinatorial results, they serve directly to help the structure theory to become as it is. So, and of course, when you study algebras, you have to choose which are the problems. I'll simply mention three main problems. The first problem is what kind of polynomial identities satisfy interesting and important algebras. Of course, here interesting and important is something which is not very well fixed. You can say this is interesting and important for me, but I think nevertheless there are some objects which are important for all mathematics. The second question is just the opposite. What can we say about algebras satisfying some special polynomial identities? Special not in Jordan's sense, but explicitly given and interesting from some point of view. And of course the third question is, I want to mention, this is what can we say about the algebra if we know only that it is PI. So we know that we have a very small piece of information. We know only that the algebra satisfies some kind of polynomial identity and nothing more. So what can you say about the algebra? Okay, maybe this question is something what you can say about the function if you know that the function is continuous, for example. So, and of course, the first place here, the first question, I think that one of the most attractive objects in ring theory, these are the matrices. So I'll start with something which was also historically about polynomial identities of matrices. So for me, I fix Mn over K. K is any field. And the first theorem was, which I want to present, this is the so-called Amitur-Levitsky theorem. I have two theorems here. Which is the following. The matrix algebra satisfies the standard identity S twice n equals 0. And no polynomial identities of lower degree, of degree less than twice n. There is something more I want to add after this, but I'll say this in the form in a moment. So, the Mitur-Levitsky theorem, it has several different proofs. It was proved in 1950. Probably some of you have seen a Mitur. And once I asked him, I saw him only 3 times in my life. And I asked him how you prove this theorem because Levitsky was an advisor of Mitura told, oh, we had to walk in the street. So, but the theorem, you see, since the matrix algebra is of dimension n squared, then it satisfies the standard polynomial of dimension n squared plus 1 equals 0. So this is some polynomial identity of high degree. So here the question is that it satisfies something which is of degree much smaller than n squared. And there are several proofs. The first proof, the first proof, the original proof by Mitur and Levitsky, it was based on some induction plus inductive, okay, I write here clever combinatorial arguments. There is another proof by Swan, which was based on graph theory. There is a proof by Constant. This is some cohomological arguments. There is another proof, 2 proofs, by Razmiswov. This uses the Kerry-Hamilton theorem. There is a proof by Rosset, which uses Grassmann algebra. There is another proof, which is by Szigeti, Tutzer, and Reves. I have to check the spelling of Reves because this is Hungarian. So this proof uses another argument, another graph theory, which is different theory, which is different. The arguments are different from the arguments here. So it's a good idea to have a master student and to give him or her to prove, to have all these proofs of the Mitur-Levitsky theorem. I did once, but without the proof by Constant, with one of my students. So here, maybe I give a short discussion about the proof by Swan, and then I go to the proof by Rosset. So, idea of the proof of Swan. I think it uses some arguments which originally were due to Schutzenberger. about treating. So you see, if you have a matrix unit Uij, you can treat this matrix unit as an oriented edge in the graph when you have here I and j. And if you have a product Eij and Ekl, you have the corresponding edges. This is K. This is equal to 0 if j is not equal to k, and this is equal to Eij if j is equal to k. So in the first case you have such a situation, in the second case you have such a situation. So this is Ijk, and you have a path of length 2 in the graph.
EIL, Vesselin.
Oh, sorry. Okay, this should be K and this should be L. So not only I be a movie star, but also you, because of the comment. So you simply have a graph with n vertices, 1, 2, etc. n. And if you have a matrix unit, you have a set of matrix units A1, J1, EI2, J2, EIP, JP. Then you put the correspondence a graph G with edges, with oriented edges, starting from IK to JK. And now you see, if you have a product of these elements, you have a product I1, J1, EIP, JP, which is not 0, you simply have a path in the graph which is Eulerian, in the sense that it passed through each edge exactly once. So it passed, the path passes through each edge exactly once.